Right. Good morning, everyone. Thank you for having me. Thank you, Carlos. My name is Ahmed Hosni, and I do applied machine learning research at Dana-Farber Cancer Institute and Harvard Medical School. And in this talk, we'll be introducing some intuition behind neural networks, why and how they work. And this talk is really meant as a high-level introduction, covering a lot of aspects. And the idea is to give you enough information to choose the methods that are most applicable to your problems. And as we've seen in previous talks earlier this morning, we are slowly moving away from the so-called expert systems that had varying degrees of clinical utility to more advanced methods that in very few instances start to match human level performance. And this shift is mainly fueled by the underlying methods themselves, where we've replaced the combination of feature engineering or handcrafting plus traditional machine learning with deep learning methods that learn from experience and thus identify the relevant features automatically. And so in this talk, we'll be getting to understand the intuition behind neural networks. We'll explore how these systems learn. And finally, we'll be able to identify the methods and best practices for training them. We'll start with a little refresher. There are really four major components to most machine learning setups. We need data to infer from. We need a hypothesis of how this data might be represented in order to serve some sort of prediction purpose. We need to be able to measure how happy we are with the performance of the model. So cost, error, loss are all used interchangeably in this case. And at the same time, we also need to know how we can reach happier states. And therefore, we need an optimizer to optimize our loss function, essentially making us happier with the model. So let's apply this checklist to a simple logistic regression problem. So in this case, we have a data set, a toy data set of benign and malignant tumors with two features, nodule concavity and a nodule radius. And so we have our data. So that's the first item in our checklist. We then formulate a hypothesis. We think maybe our data is linearly separable. Let's then decide to use a simple linear logistic regression model with a line equation wx plus b to model the data. And so to start, we really don't know where this line should go. And we have to randomly initialize the parameters. In this case, we have two parameters, the weight or the slope of the line w and the bias b in the intercept. And we make an assumption here that everything above the line should be red, should be malignant, and everything underneath should be benign. And this is where we can start to measure our happiness and define a loss function. So in this specific case, we'll use log loss, which obviously penalizes the points that were misclassified and allows us to put a value on the loss. Now, eventually, our goal is to correctly classify all the points, or hopefully most of them. And so we need to minimize this loss. And for that, we'll be using gradient descent, which is our optimizer. And we'll be essentially calculating the gradient of the loss function with respect to each of these two variables. And so we are assuming that the loss function here is well-behaved, it's nice and convex, just a single global minimum for this example. And so the gradient will point us to the direction in which we need to shift the parameters, the weight and the bias, in order to minimize the loss. And this eventually gives us new values for the parameters, and this allows us to move the line to a new position. And we can observe that the loss during this process has indeed been reduced, so we're kind of going in the right direction. And we can repeat the entire process over and over again to get a new loss value, and recalculate the gradient at this given line location, and move the line again. So eventually minimizing the loss and correctly classifying the points. Now let's take a closer look at our hypothesis here. Now, assuming that this model is deployed in the wild, or we collect new data points and we want to incorporate it into the model. And so we get a new data point here that has a very high nodule radius, and we know that the ground truth for this point to be malignant, but apparently our model is classifying it as benign. Or maybe the same could happen with a malignant data point with a very high nodule concavity. So it seems at this point that our initial hypothesis had kind of oversimplified the data space a little bit. So we need to do something about this, and then maybe our data should actually look something like that. And the line does not help anymore. So we look at other options, and yeah, maybe a circle would do. Maybe we can use a circle to solve this problem. But let's try to look at something a bit more flexible and scalable. Let's do two lines. Let's call them line A and line B, two separators basically. And what this does is that it essentially divides our data space into 4 quadrants. And given a new data point, let's say we have a point in this benign quadrant over here. This is difficult. That this allows us to ask the model a set of questions in order to arrive at a classification for this point. Okay, let me turn this back. Which direction does it go? Down? Oh, there you go. Thank you. So let's ask the model a few questions in order to arrive at classification for this point. We ask line A if this given point is over or under the line, and we get 2 yeses in the corresponding quadrants. And we also ask line B the same question, over or under, and we also get yes, no answers in this case. And the third question we're going to ask is check if the responses to both the 2 past questions is a yes. And so our new data point is indeed classified as benign. Now let's take this and represent this model in a graph format. And so what we'll do is put each line in a node on its own, and we'll, with each node, essentially asking a specific question, line over or under. And what we'll do is essentially provide each node with the 2 features, the radius and concavity in this case, in order to plot a new point which we would like to classify, denoted here by the X. The nodes eventually answer these respective questions and spits out two yeses in this case. And we will then have a third node that will take the inputs of the 2 previous nodes and perform a very simple logic AND operator. So if they're both yes, then this node would also spit out a yes. And so we've classified this given data point as benign. And so you might be wondering here that this AND node is doing something different than the 2 other nodes in the previous layer. So let's look a little bit closer at this node. And if you dig deeper and if you convert these nodes into kind of the inputs to the node into a binary 0-1 system, you'll find that the AND node is also performing its own question answering based on a linear separator. And so if we arrange the inputs to this graph, the radius and the concavity into a column, we really end up with a neural network. And we have our inputs with the features organized in a column. We have one hidden layer. This is essentially where the magic happens. And an output layer that gives us predictions. And if we look under the hood, we'll find that each node is performing a simple linear operation, multiplying the input value with the corresponding weight and adding all these up to a bias. After that, an activation function is then applied to each node. In this case, the activation function is a step function, and this function decides if a node will fire or not. And so activation functions are really very important in neural networks. They tell us whether the information that the node is receiving is relevant or it should be ignored. Activation functions also help us approximate very complex nonlinear relationships in data. And so you could imagine that a neural network without activation functions is simply a linear regression model. We'll get into activation a little bit later, but let's look a little bit closer at this AND operator. The AND operator handles a very simple linearly separable problem. There are other logical operators as well. You also have the OR operator that only fires if at least one of the inputs is a 1. Again, this is a linearly separable problem. We also have the exclusive OR or XOR, and this one fires if exactly one of its inputs is a 1. And we have a problem here because obviously the problem is not linearly separable. So let's look closer at this operator, and what we'll try to do here is stack nodes and see if we can reproduce this nonlinear function. We have here a neural network with 2 hidden layers, an input and an output. And let's just focus on the thicker connections here, which donate heavier weights. And let's ignore the faint connections in the background. Let's see if we can get a positive activation for outputs 0 and 1. So let's input these into the network. The pass-through, as the name suggests, is just a pass-through operation. The NOT operator takes one input and flips it, basically. So the 0 goes in, comes out as 0 and 1 on the other side, and the 1 goes in, comes out as, again, 0 and 1 on the other side. Moving on to the second hidden layer, the 2 AND operators here will only fire if both inputs are 1. So we get a 0 from the first AND operator and a 1 from the second AND operator. Finally, we have the OR operator, which detects a 1 its input and spits out a 1. So the take-home message here is that stacking units will allow us to model linearly inseparable data. And this is something that's impossible with regression models. And okay, that's great. The only problem here that until recently, we couldn't have this network really learn on its own. And the reason is that the activation functions that we're using, the step functions, are non-differentiable and obviously also non-continuous. As you can see here, the weights, the heavy and the fainted connections, these have been fine-tuned by human basically. And since we now started talking about learning, let's move on to the next session. Or next section, I guess. Let's talk about how neural networks learn. It was back in '86 that Jeffrey Hinton and colleagues proposed that we replace the step function in neural networks by other differentiable functions that are continuous. Here, they proposed a sigmoid function, but it could really be anything else. And once you do that, then it becomes really possible to train a network using gradient descent and backpropagation. And to see this in action and how this works, let's look at another toy example. We'll be using the iris dataset. It's probably one of the most popular datasets in machine learning. We have 4 features, the sepal length and width and the petal length and width. And we need to classify each point as one of 3 classes of the iris flower, either versicolor or setosa or virginica. So let's revisit our machine learning checklist that we started with and see how we're doing on that regard. So we have our data set, we have 4 features, and we have 3 labels in this case, so that's taken care of. In this case, we've made a hypothesis. We will do a 3-layer network with a single hidden layer. We decide to have sigmoid activations on the hidden nodes. And this will give us an activation value between 0 and 1 for the nodes in light blue here. And we also decide on a softmax activation on the output layer. Now, the softmax is essentially the normalized exponential. And while the sigmoid operates on a single node, the softmax operates on the entire layer. And so the question here is, why not just use sigmoids on the final layer as well? I see the room is not set up for questions during the talk. So if you had a chance to think about it, we could have replaced the output here with a single node with a sigmoid activation. So instead of having 3 nodes with softmax in the output layer, we can have a single node with sigmoid. And now that would only work if we had a 2-class problem. In this case, we have a multi-class problem, we have 3 classes, and so using the sigmoid does not make sense. And that's why we need softmax, as softmax is essentially a generalization of sigmoid. Okay, let's look at our loss function now. For our loss function, we'll be using cross entropy, and cross entropy will take the input, the ground truth labels, and will also take the predictions. And since we want to maximize the likelihood or the log likelihood, and since log is a monotonic function, so we eventually want to do is minimize the negative log of the likelihood. And we'll see this in action in just a second. On our checklist, we have our optimizer, finally, our gradient descent. And the best analogy for gradient descent is being stranded on a mountain, and it's really foggy. Visibility is only a few feet in front of you, and you have to use local information in terms of slope, whatever you can see, in order to reach the base of the mountain. And we'll see this in action as well. Now our checklist is complete. We can now start training the network. And so the first thing we need to do is we need to randomly initialize the parameters donated here by the connections. These are the weights and the biases in the network. Now we input a single data point. We have the 4 features of a given data point together with the corresponding labels. Here what we do is we one-hot encode the label, and this gives us a vector with all zeros except for 1 at the correct label. So in this case, that would be the iris versicolor. We then forward propagate the inputs through the network. And here we multiply the inputs by the weights and add the biases. And then we apply the nonlinearity through the given respective activation functions. So we know that sigmoids will always give us a value between 0 and 1 in the hidden layer. This looks about right. The softmax will give us a normalized vector in the output. So these should all add up to 1. That looks right. We can see here that the network gave us, with obviously the random initialization, the network gave us a maximum probability of 55 or 0.55 for the second class. So I mean, we know that it's wrong, but let's now go ahead and quantify how off it was. And this is where we actually calculate the loss. So we only care about the probability of the correct class here, which is the versicolor, the first one. And if we take the negative log of that value, that gives us 0.82 as our loss value. Now let's go ahead and assume a best case scenario in this case. Assume that the network has predicted the first class with 100% probability. So that would be minus log of 1, which is 0. And so, okay, great. Our loss function is working as it should. Let's look at the worst case scenario just to be sure. Worst case scenario is if the network predicts the correct class with a 0 probability. And if we take the negative log of 0, that gives us negative infinity, which is infinity. Great. So if our network is doing really bad, then we get an infinity loss. Okay, so now that we've quantified loss, let's move on to backpropagation. And you can think of the amount by which you need to shift the weights as being proportional to the gradient. And actually, since the gradient points up, then we actually need the negative of the gradient in order to descend the mountain. So assume a node with a larger gradient with respect to the loss is going to contribute a larger change to the loss. And so in this way, we can assign blame for the loss to each node. The larger the gradient is for a given node, the more blame it gets for the final loss, whether positively or negatively. And the more blame a node has, the more it will obviously be updated, the more we need to shift it in the right direction. And so the gradient here is nothing but the partial derivative of the loss function with respect to that specific weight. And the size of the step that we take in that direction is denoted by the eta here. And eta is the learning rate. It's probably, arguably, one of the most important hyperparameters to tune in neural networks. And before we dive into backpropagation, it really helps to think of the network as a function of functions. And so we have the output layer here in green, which takes as input the hidden layer, which in turn takes as input the features themselves. And this means that we have a composite function, and for that we can use the chain rule. to differentiate. So let's look at a specific example here. Let's say we want to calculate the change in Wn, which is one of the five weights of this particular node for some given input. And we have our loss function over here denoted in L. And so the gradient will be the derivative of the loss function with respect to that weight. And so we can start from loss and backpropagate all the way to Wn using the chain rule. Now remember that within each node there are two operations. There is a linear operation and there is a nonlinear one which happens through the activations. So the gradient will be the derivative of the loss with respect to the softmax function multiplied by the derivative of the softmax with respect to the linear operation that's happening in node n multiplied by the linear operation of node n in respect to the weight. And that's how we use the chain rule to propagate back and identify a delta for that specific weight, the amount of shift that needs to happen in either direction. Let's look at another example a little bit further down in the network. So in this case, we want to be able to quantify the shift in Wm, which is one of the weights for node m. And again, using the chain rule, we can start from the loss and backpropagate towards that weight. So we have the loss with respect to softmax with respect to linear n with respect to sigmoid m, which is the activation function in the sigmoid, and then the sigmoid with respect to the linear operation in m, and finally the linear m linear with respect to the weight in m. And as you can see, we're doing more and more multiplications as we go deeper and get closer to the inputs. And now that we've calculated the changes in the weights, we simply just update them. And we repeat steps 2 through 5 over and over. And so this kind of forward and backward pass is referred to as a step. And notice here that we're using, just for illustration purposes, we're using a single data point. And what we would normally do is we would use the entire data set. And so the inputs the input would really be a matrix instead of a single 1D vector. I think that the IRIS data set has 50 samples per class, so that's 150 data points. Okay, not bad, we can deal with that. Unfortunately, this is not scalable at all, because you can imagine having a data set with multiple data points. So how would that work? How can we fit the entire data set into the network? And this is really where stochastic gradient descent comes in. And so just training on the entire data set, that's your vanilla gradient descent. Stochastic gradient descent allows us to train on a randomly selected subset of the data set during each step. And so the assumption here is that we're drawing samples that are independent and identically distributed. These are random samples that are from a fixed but unknown distribution. You also have, for completeness, you also have online gradient descent, where you're training on one sample at a time. Intuitively, this might not make a lot of sense, but you can imagine being in an industrial setting where you have a model that's been trained on millions of data points, and you have new data points, a single data point that you would like to incorporate into the model. So you would use online gradient descent. But most likely, you'll be using stochastic gradient descent or SGD for short. And so in addition to the learning rate, the eta that we've introduced, there are two other hyperparameters that are specific to SGD or stochastic gradient descent. The first is batch size, so the number of data points to sample every time, as well as the number of epochs. The number of epochs is the number of times to shuffle through the entire data set. So imagine you have a data set of 100 samples, so a batch size of 10, then you would eventually need 10 steps to go through one epoch to shuffle through the entire data set. And since we're talking about hyperparameters now, let's move on to the final section of this presentation. Let's talk about training neural networks. So as we've seen in Carlos's presentation, the general aim is to find the perfect fit. When you're avoiding underfitting, you have a large bias towards the left side of the graph, and you're avoiding overfitting, you have a large variance towards the right side of the graph. And this is the dreadful kind of bias-variance trade-off. You have here your training loss in dashed blue line, and you can consider the green line to be your loss potentially on an independent validation data set. And the moment you start overfitting on the validation data set, you can choose to stop your training, which will be somewhere around the red line, which is the optimal capacity. Now, bear in mind that even though you're not training directly on the validation data set, you are using the validation data set to tune your model. And so the more you do that, the more the training and validation data sets actually become one. So that's something to watch out for. And at this point, we should also make a distinction between parameters in terms of weights and biases in the model. And hyperparameters are really the knobs that you use to tune your model. And within hyperparameters, we have model-specific parameters and optimizer-specific parameters. I think we're already familiar with the optimizer-specific parameters. So let's dive into the model-specific parameters. First, most obvious one is the number of layers and number of units per layer in a network. And this is really highly dependent on the data and how non-linear solvable your problem is. You can go as deep as you want. This specific network has 27 layers. And there are really two strategies that one can follow here. You can either start deep. So you basically overfit your model on purpose, and what you end up doing is pruning to get rid of excess layers as you fine-tune the model. Another approach, which I personally prefer, is to start shallow. You start very shallow, underfitting your model, and keep adding parameters and layers as needed. Now let's talk about activations a little bit. We've already seen the basic step function. And we know we can't use it because it's not differentiable, and we can't train networks. We've also looked at the sigmoid. Sigmoid is nice and smooth. It has very good activations for inputs that are closer to 0. The inputs are always bound between 0 and 1, so we don't have crazy outputs happening. Unfortunately, they do suffer from the vanishing gradient problem. And so as we've seen with the iris network, the further you backpropagate, the more multiplications you end up doing. And this results in very, very tiny updates to the weights. And so effectively your network can stop learning. And this is a major, the vanishing problem is a major issue with training neural networks. We also have the hyperbolic tangent. So it is essentially a scaled version of the sigmoid. It has stronger activations since it's scaled. At the same time, it still suffers from the vanishing gradient problem. Now we have the rectified linear units, and the ReLUs. They only activate in one direction. And as you can imagine, you get sparse and efficient activations in this case. This is, for instance, in contrast to the sigmoid that is always activated. The ReLU is only activated in the positive direction. One drawback of the ReLU is that it can kill a specific node permanently. So if the inputs to the node always remain in the negative direction, then this node will never file. So it's a dead node essentially. Another problem with the ReLU is that it's not bound in the positive direction, which in some cases can cause exploding gradients. We then have the leaky version of the ReLU, which attempts to solve the dead node problem by introducing a small gradient in the negative direction. And finally, we have the exponential linear units, or ELUs. And they introduce a tiny exponent in the negative direction, and that gives the node a bit more capacity in that area. Now, obviously, because you need to calculate the exponents, it's a little bit more expensive. It's more likely that you will be experimenting with one of these three activations in your works. All right, let's move on to initializations. And you can imagine that initializing a model with zeros, you end up stuck in a saddle point. If you initialize with constants, it becomes really difficult to break the network symmetry. And if you initialize with very large values, then these values usually end up having tiny updates, and hence you get a very slow convergence. And so we can use the same mountain analogy that we used for gradient descent. So you and your friends are on a helicopter and you're being dropped on a mountain. In one scenario, you're all dropped at the same spot, and in another scenario, you're being dropped at different locations. And assuming you have some means of communication, it is more likely that more of you will make it to the base of the mountain in the second scenario. So these initializations are very, very important aspects of models. And so in this toy example, we experimented with different initializations that were drawn from different distributions. And here we have our training loss curves. We have the step or time on the x-axis and the training loss on the y-axis. And you can see here that different initializations can heavily influence your results. It is quite common that random small values centered around 0 usually give the best or make the best initializations. Would also like to point out to a couple of interesting initialization methods here, namely the Xavier and the Hill methods. These methods drove samples from distributions with parameters that are based on input and output sizes to that specific layer. So they're location dependent. And essentially the weights in every layer are drawn from a different distribution. And these two methods specifically are quite common and being used a lot as well. Loss functions, really the choice here will depend on your problem at hand. So for regression problems, you might use something like mean squared error. For the multi-class classification, as we've seen with the IRIS dataset, you probably use cross-entropy, categorical cross-entropy. And if you're doing a pixel classification problem, as in the case with the image segmentation, you might use the dice coefficient or one of its variants. And for those of you sitting through the workshop tomorrow, we'll be having a segmentation tutorial that will be using the dice coefficient. All right, let's look at optimizers now. We've looked at the stochastic gradient descent. You could probably add momentum to that. And what the momentum does is that it accelerates the descent in the relevant direction. And then at the same time, it dampens the oscillations. Other types of optimizers that are quite popular is the adaptive gradient, or ADAGRAD for short. And this optimizer is interesting because it has parameter-specific learning rates. So it assigns a different learning rate per parameter. And these are adapted relative to how frequent a parameter is being updated during training. So for example, the more updates a parameter receives, the smaller future updates will be. And for this reason, it's really well suited for dealing with sparse data. We also have the root mean square propagation. This was developed by Geoffrey Hinton. It's not even published, I think, and people end up citing it from one of his lecture notes. And the idea here is to divide the learning rate for a specific weight by a running average of the magnitudes of recent gradients for that weight. And you can see here how each optimizer behaves differently. Momentum tends to overshoot the minimum here a little bit. And eventually the network fitting process is highly empirical and highly based on trial and error. So it's really experimentation to see which fits your problem best. All right. You might be familiar with regularizations from other machine learning methods. And in regularization, we essentially add a term to the loss function in order to prevent the coefficients from fitting so perfectly, essentially. And this essentially penalizes the large weights. So it lowers the model capacity while leaving it flexible enough. And if you've ever played whack-a-mole in an arcade, then that's exactly what regularization does. You want to learn uniformly from all nodes as opposed to just learning from a few. And another analogy that was the way it was explained to me is you have a teacher in a classroom. The teacher asks a question and students raise their hands. You always have students that raise their hands all the time, and you have someone sitting at the back who's a little bit shy. And so what the teacher does is that they prevent the more active students from raising their hands or from answering. And this gives an opportunity for others to learn as well. And this is what essentially regularization is doing. Another regularization method that's really popular in neural networks is dropout. And this involves completely removing a random fraction of nodes in the network together with their associated connections. Now, intuitively, how could this prevent overfitting? I mean, here we could use the whack-a-mole analogy, but it's a little bit different because we're not selective. We don't care about the node's activity when we drop them. We just drop them randomly. The idea here is that with each step, forward and backward pass, we drop different nodes. And so we essentially have a different architecture every time. And this resembles building multiple models, an ensemble of models, and averaging them out. And this really helps us avoid a single architecture overfitting on our data. And so dropout is only applied during training and not during testing. All right, another popular technique is batch normalization. And as you can imagine, as the learning progresses, the distribution of layer inputs changes due to the parameter updates. Now, as a result, this can result in inputs that are being in the nonlinear regime of the activation function. And this slows down the learning. And in this specific instance, the authors refer to this problem as the internal covariance shift. And batch normalization fixes this problem by normalizing the inputs to each layer individually during training and during testing as well. And if you've ever played telephone, as a child or as an adult, then you know exactly what batch normalization does. And you can imagine the game being conducted, say, in English. Everyone has a different accent, and the sentence at the beginning is completely different than the sentence at the end. So what batch normalization does is that it essentially translates the sentence into a standard accent each time it is being passed from one person to the other. And you essentially try to get the best approximation of the output, avoiding all distribution shifts throughout training. Now let's look at the optimizer-specific parameters. We're already very familiar with them. We discussed learning rate. Learning rates usually work with multiples of 10. A very small learning rate would cause very slow conversions, potentially days or weeks of training. On the other hand, a very high learning rate would overshoot the minimum of the function. What you ideally want is to apply decay to your learning rate, and this works quite well in most instances, where you gradually decrease the learning rate in order to achieve optimum performance. So you essentially take large steps when you need them and smaller ones closer to the minimum. Batch size, we usually go with base of 2. This makes things easier with memory calculations, which we'll see in the next session. Learning rate and batch size go hand in hand. So the bigger the batch size, the bigger the learning rate should be. And this is something that a lot of people tend to overlook. Bigger batch size means that you have more confidence in the direction of your descent. So this means that you take a larger step in that direction. So it intuitively makes sense. Number of epochs is really problem specific, and one approach that we touched on earlier is early stopping, and so you can avoid overfitting on a validation data set. Monitoring your training loss curves will really help you decide on the number of epochs, and this brings us to training loss curves. Training loss curves really offer you a great view into how your model is performing during training. So Andrej Karpathy, who's I think now the head of AI at Tesla, he had a blog that had training losses only. And so if you ask, they'll tell you, oh well, your loss curves should look something like that. So you have step or time on the x-axis, training loss on the y, And you'll notice that both these axes are unitless, meaning that the process is really highly empirical. It's very difficult to benchmark. So for argument's sake, let's assume this is your ideal curve. And let's look at how it might look otherwise in different situations. So assuming you have this new learning curve in red, so what might have caused this? Think in terms of learning rate. It's clear that we have a higher learning rate in this case. Essentially, the higher learning rate allows us to learn faster in the beginning, but it doesn't allow us to descend further as we progress through the training process. Let's look at another one. Here we have a low learning rate. A lower learning rate means that it is much slower to converge. What about here? Here we essentially have exploding gradients. So the loss function is exploding and we have a very high learning rate. What about here? If you remember initializations are really, really important. And a bad initialization means that it might take the model some time to actually start descending. So it might be, might start going around the loss function without any descent until it finally catches up to the descent. Now, what about here? I mean, the loss curves will always be a bit noisy because you're using stochastic gradient descent. But what might introduce more noise into the curve? Think batch size. So a very small batch size would actually introduce more noise. Just think about it. A small batch size is not enough to explain the variance that is happening across the entire data set. So you end up taking steps in different directions. And so in stochastic gradient descent, you're computing the gradient of the loss function with respect to a single batch, but you're calculating the loss over the entire training examples. And so generally, your loss will have a general downward trend, but there will be some deviations here and there as you're dealing with different batches. And finally, finally, we have this curve here. You have a training loss that decreases and increases, and this might really hint at a large learning rate. And a situation like this would be a very good candidate for the learning rate decay that we looked at earlier. Thank you very much.